Hello, guys. Welcome to the Data Science Mentor program session. And so it's the Data Science Mentor program, and this is the Data Science Mentor session. My name is Pablo. I am a data science professional. I am a Google developer expert for data and cloud. And in the Data Science Mentor um, session, what I do is introduce data science to every beginner in a very, very interesting fashion that makes it easy for them to go through the learning curve and then introduce examples, intuitive examples. Part of the goal is to prepare anyone who wants to get into the AI and machine learning side of things to be grounded in fundamentals. And in today's session, we're covering introduction to machine learning, and we're looking at unsupervised machine learning techniques. Now, unsupervised machine learning techniques are techniques that focus on the whole of the data rather than a focus on the output. Output meaning I'm not taking data and thinking about what predictions I can make out of it, but rather let me finding the essence of the data being the important aspect. Now, when we say essence, what we mean is looking at groups or clusters of your data or reducing how much data you have in terms of dimensionality so as to see if you can find insights. And so this is, a huge departure from supervised machine learning techniques where you have data points and you have rows and columns, and there's a focus on rows and columns, and also a focus on a certain column that is our output. That's what we're making our predictions for. Right. So let's lock in. Right. So the first thing I'm going to do is, and just to set the background, we're using a Jupyter notebook. We're using a Jupyter notebook. Let me get my annotator. Right. So we're using the Jupyter notebook in the cloud, so which is the Google Colab. So we're going to be taking advantage of Google's compute resources. So we're going to be taking advantage of, right? So we're already provisioned, and we are also taking advantage of Google's high-level large language model, Gemini. So we have a Gemini assistant. So at every point we make use of AI, just helps us to prevent context switching. All right, so the thing I'm going to get started with is at every point, I don't write code. I do a lot of explanations because it's typically, it's really, really important that we understand what the concepts, the abstract concept is all about before we now engage into, breaking things down. So the first question would be, what is manifold learning? Right. Hold on. Let me put a question mark there. So what is manifold learning? So let me break it down. Manifold learning is a way of discovering hidden patterns in data or hidden shapes in data. So it is a technique for discovering hidden shapes in data. Now, this definition is typically technical because you need to ask yourself, what does it mean discovering hidden shapes in data? Now, data, so again, another intuitive way of saying it is we have high dimensional data. So when we say high dimensional data, we could be talking about data that has different dimensions, like different rows and columns. Right? We have high dimensional data, right? However, we have high dimensional data. However, it often has a simpler structure underneath. So it often has a simpler structure underneath. So that simpler structure is what we're looking out for. Now, if I have to break it down, so it's just to make it, so as to make it simpler again, is if you think about data as a bit of paper, and this paper is, this large paper, maybe, folded, the paper is crumpled, right? There is something in that date, in this crumpled paper, that makes sense. And the only way to figure this out is is by flattening the paper just to see what's in it. You see that? So data is often that way. So we might have data with 100 columns, right? So there's a lot of dimensions to the data, but you're saying, how can I flatten this data so I can see things clearly? So that's basically it, right? So in essence, what we're going to do is that learning manifold learning helps us to do a lot of stuff. So let's say it helps us to unfold the data, which is the paper we're talking about. It helps us to flatten the data. And finally, with all this, we see patterns that have always, that was always there. So that's basically what it's like. Right, again, think about it. A crumpled paper. Say the crumpled paper is a map, right? So the crumpled, is this correct? Patterns that were always there. So say a crumpled paper is a map, and you want to basically find your way around, and you see the map has been rolled and on. Now, part of what you're to do is to say that, how do I know where to go to? You have to find a way to put the map, make the map flat, right? And so for you to be able to, see a lot, because once all together, you have overlapping layers. Now, so if you think about this concept, you now think about, if I had data and I have to solve a problem, I need insights from this data. That means I need to unroll the data, make it flat. So that's the concept behind the manifold learning. There's a lot of things, right? There are lots of use cases. So let me put this. I like to write down these use cases a lot, to write stuff down so that it works. So when you're watching this again, you can make sense of it. So here we write use cases. We have customer segmentation. I think about it. Customer might have so many records, but you basically want to, you want to reveal a lot about this regardless of the many records. So they have age, location, income, browsing habits, spending habits, device type. What do you do to these data to make you see literally everything like in a flat surface? So that's one. There's customer segmentation. And in biology, there's something trying to understand. In biology and medicine, we're looking at this millions of cells, and you're looking at millions of cells, but this patient has certain diseases, and you're thinking, how can you look through how can you look through this data in order to find what may be wrong with this individual or whoever is sick, right? So in essence, that's here the best way to look at this is to say biology slash medicine. So with biology and medicine, you're trying to solve, you're trying to find an ailment or try to understand what's wrong with folks. But there's a lot of information like cells, their diagnosis, their history, right? So how do you put all this in a way that you can tell what's wrong with the patient? So that's another use case. There's also image compression, right? With image compression, you're trying to, you know, find a way to get an image to look really great so that we can see a whole lot about the image and all. So in essence, we want to be able to visualize the photo and be able to see if it makes a lot of sense. Right. So that's that one. So let me just have this closed up. Now the question is, why do we need manifold learning? So I think that's the very another way to look at it. Why do we need manifold learning? So that will be the topic here. Why do we need manifold learning? Right. So again, we need to proper visualization of data. Because they are hidden patterns, so we need proper visualization of data. Because the idea is that high dimensional data would always hide somewhere. Let me put this here. High dimensional data lies on low dimensional data, or rather, lies on low dimensional shapes. And so it's important that we have a manifold learning that makes us see the proper visualization of data. We can also, with that, we can also cluster data. With that, we can reduce noise. Look, whenever you have data, what you have is the signal and you have the noise. Uh, your job is to, sift the noise from the signal, right? And also one final part, it helps, it supports ML technique, the ML workflows. I don't say workflow, like you get the data, um, and you're able to see the data in many ways, and this could help you do a lot of either pre-processing, a lot of wrangling, a lot of, taking away the noise from the real data that you're looking for. So that's what we have. That's what we're doing. Now, the next thing we want to do is we need to now get to do the technical bits, right? We need to do the technical bits. Now, what we want to do is we want to, I would like to show you stuff. Just a second. So what I'm going to do is I'm going to show you what it looks like when we're talking about manifold learning. So what I'm going to do is I am going to visualize. I'm going to visualize the data and just to make an explanation. So what I'm doing at the moment is I'll upload the data, then I can show that to you over. Oh, okay. So what I could do is, so let me say, display. I'm going to use Gemini here. Display an image that illustrates manifold learning for a non-technical audience. Right. So display an image that illustrates for a non-technical audience. So that's going to come up in a bit. So that way we could get to see what we're looking for. Yeah, I can generate a markdown cell with an image, please. Please replace it with the actual. Okay, you know what? I'll do that. I will do that. So I'll replace the image with an actual URL. Yeah, lovely. All right. Let me do that now. And then, so what I'm going to do is I'll come over here because I have that. So once I do this, then I can now replace this here with a link. So I have an image. So let me pick this and I'll copy the part. And I come over here and I put the your URL image here. This is supposed to be it. Okay. Guess what I'm going to do? I'm just going to import let me import IPython for image display. That's what I'm going to do. IPython for image display. So can I get that? Yes, thank you so much. I used that. So what I'm going to do now is I am not going to say image and I'll open brackets and I'll write the file name and here. And so I run this. Now, basically, this is what we are looking at. So apologies that it took a little bit of time, but now, so if we think about what we're going to be doing, if we think about it in terms of we are looking at an image and say this is a folded paper, Now, it was interesting that I introduced this over here, which is the principal component analysis. And for principal component analysis, what we try to do is we're trying to like find the different clusters for our data to see if we can make sense of it. But another thing I didn't say is when you work with um, manifold learning, it's work with data that is non-linear, right? Um, yes, it works best with non-linear data. So this is important. Now, for PCA, the data has to be linear, so there has to be some sort of like a relationship that exists, right? And but here you can see that if we try to break them down into two components or three components, we still there's barely any insight you can get from it, right? But if with manifold, you sort of unroll the data and just get to see what's in it. So this is basically the idea of what we talk about when we use manifold learning. So think about a rumpled map. If it's rumpled and you say you want to break it into two components or three components based on the dimension, this is what principal component analysis might want to give you. But with manifold learning, it unrolls it and just shows you what you need to see. And a lot of the data we work with are like that. Right. Now, here is now the technical bit of what we're going to be doing. We are now going to build on this itself. So here, the first thing is we're going to illustrate this same role that I've showed you here. I'm going to illustrate them with code. So let's illustrate the Swiss role. Now, to do that, what I will do is I will import visualization libraries. I'll import the visualization libraries. So that's the what I'm going to do. Now to do that, I'm going to import matplotlib. Yes, I import matplotlib as that. I would also import them from sklearn datasets. I'm going to import the Swiss role. So these are the two things I want to make use of. Next is I am going to generate 1,500 points rolled up in a spiral. So again, I'm right. I'll generate 1,500 points rolled up in a spiral. Yes, rolled up in a spiral. One really interesting thing when you use Google Colab, you've got the AI tool typically there to help you prevent you from context switching, right? So what we're going to do, we're going to call this X. I'll call this color. We're going to now make the Swiss row, which is what we have here. And also there's a parameter that says noise. And with noise, we want to ensure we don't have any noise whatsoever. That's one. So we have this. Next, what we're going to do is we are going to visualize in 3D the road carpet, so to speak. So here we'll visualize in 3D the Swiss. That's what we do. The first thing I'll do is to create my fig. I'll say fig.plt.figure, give it a size. And so I'll say fig size. I wouldn't want to be 10 by 10. That'll be too much. I would want it to be 12 by 6. right? So we're going to add like a subplot. No, let's make it 1 to 1. And then we're going to project a 3D of what we want. Then next, we're going to have a scatter plot that looks at what are the data we have. So it's going to break the data into 3 perspectives. And we're going to set up a color. We're also going to pick up our, yes, we're going to set up the color and then our color map. Next, the next we're going to do is we are going to set title. So we say ax.set underscore title. Yeah, so you see this makes a lot of sense. And then before we view this, we might want to say ax.view underscore init, right? So now what we want to do with this is we're going to say 4 by 72, and then we're going to visualize. So now you see, now you see what that Swiss roll looks like, right? The Swiss roll looks a lot like what we have here. This is what we have here. Now, the next thing we want to do is we want to figure out why it's not so intuitive to use principal component analysis, right? Because with the principal component analysis, we're going to say, can we find some sort of like, a linear relationship and see if we can now use that linear relationship to sort of make it into a flat roll, right? So that's what we're going to do. Then we eventually see how that's important, right, to do. So what we're going to do here is use PCA to create a flat roll. That's one. So first things first, we would have this in here. Next, what we're going to do is we'll try to flatten it using PCA, and we'll use 2 components. So let's try to flatten using PCA with 2 components, So that's what we'll do. So let's see if this makes some sense. So what I do is I write and I just sit back and see if it's going to be a help. But okay, no help. So PCA, the help will come true. So when I say PCA equals to, because it should be able to read this and say 2 components, then I can call PCA, and when I call PCA, what I'll do is end components 2. You see, it's eventually helped out. But this is not what I wanted to call it, because it would make a lot of sense. I'm going to call this XPCA. Right, so we'll run this. So now we have flattened this into like a 2-dimension, 2 components or 2. Yeah, so now if we flatten it, let's see how it looks. Now what we're going to do is plot the results. We're going to plot the results. Now when we plot the results, what we want to do is we already have our stuff going on, what we have going on. So I'll just say ax.2, and in here I'm going to add this. I'm going to look for a scatter plot for this, and I'm also going to get a scatter plot for the next one, where I put a square bracket, comma 1. With this, I say C is equal to color, and I'll run it here. Let me put this and have this done. So what we have here is XPCA that is into 2 dimensions. We have the colors. We set the title to a flattened Swiss roll. Is it flattened? Yeah. Then let's see what it looks like. A flattened switch row using PCA. And then say plt.show. And does this work? Are we missing something? What are we missing out on? This is what we're trying to show. Okay, why are we not getting this? Why? I'm wondering why. This should work. All right, let me clear and run all cells. So we're going to clear and run all cells. Okay, let me introduce this. Let me see. Yep, I just realized that I did not introduce that. So now with the flattened switch roll, this is what it looks like. Now with a flattened switch, it looks this way. And I say you got to ask yourself, okay, do you get to see any form of, do you get to see any form? So let me make it 10. Yeah. Do you get to see some form of an insight? So again, this is typically what we would have seen from here, right? Now, the next one we want to do is now to say, let's look at the success of X. Now, so here is what we're going to introduce is using manifold learning using manifold learning, basically. Let's use that. So first thing first is we are going for manifold learning. We are going to import isomap. That's what we would import. That's what we're going to be using. That's one. Next, we are going to use manifold learning to unroll the data. So use manifold learning to unroll. Right, that's what we're going to do. We're going to use it to unroll. Also, what we could do is we would use end neighbors. Now, what does the end neighbors mean? It will look at the 10 closest ways, right? Because here, what we're going to do is, yeah, so let me do, so we're going to use the parameter n underscore neighbors, and it's going to be equal to 10. So what it means is, so that's what it's going to look out for the 10 process steps for us to work with this, right? So you see that? So what we have here is we will say n neighbors, and then we can now say n underscore components, and we say 2. And so in essence, is we're going to sort of like now visualize, we're going to visualize the unrolled data. That's what we're going to do. So first things first, with my figure here, and with my figure here, I'll just basically say plt.scatter, plt.scatter, and all I want is ISO 1 and 2, the color and everything I want. I say plt.title, I'll call this a flatten. Now I'll say, yeah, okay, yes, use the manifold learning. Then any other thing, okay, let me introduce a grid. So I'll say plt dot grid. And when we say plt dot grid, which means it will work basically. Yeah, so look at that. So you can see that now we've unrolled our data. We can see if there are different things we see in our data, and typically see this is the insights we're looking for. And this insight would be interesting regardless of, if it's non-linear, it just shows us what's up with this data. Unlike here, when we tried to look at 2 components of the data for the rolled-in work, and this is what it was typically when we first got the data, the Swiss roll, and how we now looked at it in a different dimension and can now basically tell a lot about our data. So this is what it looks like if we typically want to understand what manifold learning is about. And so think about any data point you're using: customer data, age, location, gender, spending patterns, spending habits, browsing habits. Think about all that. And now think of what you can do with that data if you unroll that data and made it look flat. There'll be it's like you're reading through the data and you can find patterns for it. So that's basically what this is about, right? Yeah, and it can typically help us make sense of data. So that's what we have for today's session. If you have any questions, feel free to, drop a question in the chat or in the comment section if you feel like, or you could drop it in a private Telegram group.